right. Good evening, everybody. Welcome to C++ Online, the first edition here. My name is Andreas Fertig. I work as a trainer and consultant for C++, and today's topic of my talk is C++20's coroutines for beginners. All right. So I hope you enjoyed it. It's a real fun topic about C++20 and I think a real valuable one. Before we really dive into C++, let's start with a different language, German. I'm German. My last name is a very German word. It's used there, well, really frequently in the language, and it's translatable to English as finished, ready, complete, or completed. So it's a wonderful name. I personally like it very much. And there's this interesting story when I went to UK for CPP on C in the physical edition a couple of years ago. I arrived very late in the hotel and I was tired, so I might not be as fit as usual. And the receptionist there, we had a little chat. And at some point, he asked me, "Ready?" And I said, "I don't understand that. What does ready mean now?" He meant ready. And I said, "Sorry, I don't get it." And he said, your last name. And I was, "Oh yeah, he understands German." Of course. And ready is the translation. So he got it right and I didn't understand it. This happens. So I try to be better at that. This is what can go wrong when you cross languages. So let's stay in C++ for today or for the rest of this session. Coroutines. Let's first compare them to functions, because functions is what we know very well, right? Across all programming languages, we have functions. And a function is a very simple thing. We have a function and that calls another function. So we have a caller calling a function. That's a function call. And then this function, the callee, runs until it returns. Maybe it has no written return because it returns void. Maybe we return a number, object, whatsoever. We can have multiple returns in this function. It doesn't matter. At some point it returns, and by that it transfers control back to the caller. While this function is running, it cannot be interrupted. I'm threading aside, but this means this entire control flow gets simply paused. So we can call this function obviously as often as we want, and it will produce either the same or different result depending on the inputs. Whenever we leave a function, that means the entire state this function just calculated goes away. Okay? Every variable we declared inside that function and used for our computations, it gets destroyed. It's on the stack, and now it's up for the next caller or next function to use that part of the stack. These are functions. On the right-hand side, you can see the control flow of a coroutine, which can be totally different. So we have there a caller that places a call to a coroutine or a coroutine function. And now one property of coroutines is that they can be paused and resumed. This is very different to the model of a pure function. So in my picture here, the coroutine runs up to a certain point, and then it suspends itself and yields control back to the caller. With that yield, it can also transfer a value. It's like a function that returns multiple times, but still preserves its state. Now the caller can continue its work and at some point decide that it needs more information from the coroutine or another computation, so it resumes this coroutine at the very point where it left off. Coroutine continues running until some point it decides to yield another value to the caller. And now the caller goes gone, and it resumes the coroutine after some computations, and then the coroutine runs for some more work and finally decides to co-return. So here you see two new keywords that are available in C++20, co-yield and co-return. We will later see a third one. This is co-wait. Yield means we are transferring something out of the coroutine. As return, the difference between the two is coroutine means that the coroutine really is finished. You are not supposed to invoke it again, to resume it again. Doing so would be undefined behavior. Okay. If you compare these two control flows to each other, then we can see that a function is just a special version of a coroutine, because you can see it as a coroutine that co-returns only once. Okay, so the more general way are coroutines. They can be paused and resumed. On the function, as we used it for so many years in C++ solely, there's a specialization of a coroutine. So what are coroutines? The term coroutine itself has been well established in computer science since 1958, when it was first coined by Melvin Conway. Across programming languages, we have two different flavors of coroutines. You might have heard the term stack full or stack less coroutines. The latter one is what we have in C++. There we have stack less. And the stack full or stack less is the answer to the question, where is this information stored for a coroutine to be able to be paused and resumed? The coroutine here plays a very simple, maybe special trick. It does not store its information on the stack, at a regular stack. It stores it in a dedicated section. And this dedicated section is either on a special segment on the stack, then we're talking about stack full, or in the case of C++, it's in a different location, not on the stack, and that means on the dynamic heap. So dynamic memory is used for coroutines, or storing the coroutine frame in C++. And yes, that also means whenever you're creating a new coroutine, there is a global new to the global heap at this point. When we're talking about coroutines, we are often talking about cooperative multitasking compared to preemptive multitasking. I have the example for that later, where the two models are compared. Coroutines can help us to simplify our code. They can help us to replace function pointers, aka callbacks, making the entire code look simpler. I have seen parsers becoming readable or way more readable when we used coroutines to implement them as opposed to function pointers or whatever model there was. The reason for that is that a lot of this state maintenance code that we otherwise have, the parser is practically a finite state machine. The callbacks are some way of seeing it. So all this finite state machinery maintenance, the state that we have to maintain ourselves, otherwise, this bookkeeping is done by the coroutine. So it's off from our plate. And this is why coroutine code becomes way more readable. Okay, so this is a very, very great thing, improving our software there. There are various ways to interact with a coroutine. So first of all, we already established that coroutines can be paused and resumed. This is their primary selling point. This is what makes them great and different to usual functions. We have three new keywords in C++20, that's co-yield, co-wait, and co-return. So co-yield is an output action. Usually that is like a return where we still can resume the function, or in this specific case, the coroutine. The state of the coroutine itself, most often after that, is suspended. I'm saying most often because we can configure a lot there, but let's assume the state is suspended. Co-return is the other keyword, which is also an output action. So that means they are more or less equivalent, except for the state. Once we say co-return, I previously said that, the coroutine is ended. So this is comparable to a regular function returning. We are not supposed to invoke this coroutine or continue it again. Then we have the third keyword, the co-wait. And this is another cool way to input something into an already running function. in this specific case, a coroutine. So this is an input action, and the state of this coroutine must be suspended at this point, or it will be suspended. So it waits for more data from the outside, and then it gets resumed. You can see this like if you're passing parameters to a function, just that you are with co-wait available or able to pass data into the coroutine, so pass parameters to it while it already started, while you already invoked the function. So these are the three keywords and three functionalities we have there to interact with a coroutine. Coroutines in C++ are maybe not the easiest thing to start using them or exploring them, because coroutines in C++ are heavily customizable. This is what makes them great in the end, but it means that getting started with them, simply play around with them, for example, in Compiler Explorer, that's rather tough. So there are other languages where this part is way easier, but the C++ part then excels at the customization and priming it to what you exactly need and get the best performance out of all that. So that means we have to talk about the parts a coroutine consists of in C++. The first thing that is a must is a wrapper type. This is the return type of the coroutine's function's prototype, or the thing that your function returns. This type, this is what I call a wrapper type. With this type, we can control the coroutine from the outside world. So for example, we can resume the coroutine or get data out from it that the coroutine previously yielded to us. This is based on the assumption that this wrapper type stores a handle to this coroutine. As said previously, a coroutine causes a new because the state, the coroutine frame, is stored on the dynamic heap. So we get a pointer back, like creating an object with new, where we get a pointer back. And the same mental model applies for coroutine. When we create this coroutine, we get a handle, a pointer, essentially, to control and interact with that coroutine. And this wrapper type can store this handle, and with using it, can control, can interact with the coroutine. This is the purpose of this wrapper type. And we can make it real beautiful such that using and interacting with this coroutine feels natural, and we don't even see as users that there is a coroutine behind. The compiler then, as a second ingredient, looks for a type with the exact same name as on the slide, promise type, inside our wrapper type. So inside the return type of our coroutine, the compiler looks for a type, promise type. And with this promise type, we can control the behavior of the state machine. We can configure it. There are a lot of customization points to trim it to our needs. This type the compiler looks for inside a promise type. It can be either a type alias, a type def, or we can place the new type directly in the wrapper type declarative. We have plenty of options like for usual types. The only thing that is a must is the name here, promise type. So these are the two base components. It's really hard to get around them, I would say. You need the promise type. You can play special tricks maybe to get away with the wrapper type, but usually you have both of them. So let's consider them a must. There are two other types that are frequently used when it comes to coroutines. The first one comes into play when we use co-wait inside our coroutine. We call this, from other languages, borrowed an awaitable type. We will see an example for that later. As I said, we need it once we do a co-wait. Otherwise, it's optional, not needed. And the fourth part, the fourth element that's often used together with coroutines is an iterator. And the reason for that is that coroutines are an excellent way of implementing an infinite stream of data. So think about you holding a TCP connection to a remote site. You cannot say when the end is really there. You'd simply get data, get data, get data. The other side might close, you might close the connection, but if nobody closes it, you simply get data stream to data stream. And this is something where we usually like to iterate over the data. So iterators are often used together with coroutines, and then we have to implement an iterator part of them. I touched on that earlier. In C++, coroutine is a finite state machine. We can control this finite state machine by configuring or customizing the promise type. So this is our way to adjust the coroutine to the behavior we want. That also means there is not the one coroutine, as a lot of us want to, as I said, play around, get started with, have an early entrance. It's not there because it's designed to be customized for our needs. That means it could be that you're finding the one promise type that fits into your software. You only have one in your project, in your company, or the more likely chance you will have several promise types for several different situations trimmed for performance for each of them. The actual coroutine function, that's the one using co-yield, co-wait, and co-return for the communication with the outside world. So all of these three keywords means coroutine usually gets paused and either it send away some output or it waits for more input. So before we get started by looking at real code, here's an apology I have to make. I always feel that's necessary. It's a disclaimer. Usually I don't have disclaimers in my slides, but this time it's necessary. Please note, I tried to keep the code you will see as simple as possible. I have tried to focus on the coroutines part only. So in protection code, I would use way more public and private, as well as potential getters and setters. Additionally, I would use way more generic code in production to keep repetition slow and to get away with lesser promise types. However, for the purpose of this talk, my goal is to help you understand coroutines, and I'm very confident that it can improve the code you will see with the usual C++ best practices, okay? I'm short on slide space and all that stuff, so I wrote code that I usually wouldn't write. This especially goes for the last sentence. I teach that, but believe me, you can hire me for training and we'll tell you that. I also never declare more than one variable per line, except in this presentation for slide code. I got away several years without doing that in slide code, but for this presentation, I didn't find a better way to do it. So bear there with me, please. All right, here is our first C++ code of today's talk. It's implementing a coroutine with the name chat. So it's a very chatty coroutine, okay? At the top, in line number 1, in A there, you can see the function prototype. Its name is fun, and it returns a chat object, a chat type. You don't know anything about that. I obviously implemented it, so I know a little more. But we will come later to this type chat. This is the one that fun returns, and without knowing how chat looks like, we know because once we start looking at the body of this function, there's a co-yield, a co-wait, and even a co-return in. I managed to squeeze all three in, very cool. But by looking at the body, we know chat must be one of these wrapper types. So inside chat, the compiler must be able to find a type called promise type. So we know we are looking at some special wrapper type here without knowing the type itself. Now in the body of fun, inside our coroutine, we co-yield a std string first there in B. And then next in C, this coroutine co-waits for a std string. So this is give me more data. And lastly, in D, the coroutine co-returns another std string. So this is the entire control flow of this coroutine. Used is in down in line number 10. In E here, in line number 12, I'm calling the function fun, the coroutine, for the first time. That means here I'm seeing the new, I'm creating a new object. I can do that as often as I want or as often as I have memory for it. It's like creating a new object with new. They get this object chat back. So a wrapper types object. I call this Marco from Marco Polo. And the first thing I'm doing here is in F, I'm listening to what the coroutine says. So I'm calling Marco.listen and printing that thing out. And the next thing down in G is that whatever I heard, I answer. So Marco says answer here, invokes a member function on chat, which we will see in a moment, and it says some string. And then in line number 18, in H, we call Marco.listen again. So we listen again for what the coroutine has to say. If we run this program, then we will see that the coroutine starts by sending hello, while we then from the outside in use say, where are you? When the coroutine will reply, here. So very simple chat at this point. Now, I would be really happy if this is all I would have to show you, but as I said, it's highly customized. So here is the promise type. So this type inside the wrapper type. And you see it barely fits on the slide. And this is why in A, I decided to declare more than one variable per line. Okay, apologies for that. I also did it to make it more visible what is the in and what is the out part of our coroutine. So I have two string objects here, MSG out and MSG in. Okay. Now the rest that you're going to see are these customization points I talked about before. So the first one in B here is called unhandled exception. For all of them goes, they have to be spelled exactly like on my slide. The only thing or the only customization point that must be no except is the last one in E, fun suspend. For all others, you should adjust it to your needs or whatever is appropriate for your software. So unhandled exception in B helps us to deal with a situation where inside our coroutine we receive an exception. Because we are in some kind of a nested environment, once we receive an exception that leaves our coroutine is destroyed. So the default mode as I'm implementing it here is saying let everything crash. You can implement exception handling there. You can catch exceptions from the outside, but your coroutine in all cases is gone. I'm not going to talk more about exceptions and coroutines today. Okay. C is our starting point, get return object. This is the way of the compiler to create the wrapper type, because the promise type and the wrapper type are only related in terms of the one is in the other. The compiler doesn't know how to create this wrapper type. So how the constructor looks like, how many parameters does it take, and all that stuff. And to give us a flexible way as users, as programmers, to create this wrapper type with all different possibilities we can think of, the compiler simply calls getReturnObject. We return a type there, and inside getReturnObject, we can create that one with all the parameters this type needs. Okay, I'm using return value optimization there, or copy elision, so that will simply be created at the destination. But this is our way to create the wrapper type. This is our first interesting customization point. In D, we see the customization point initial suspend. So once a coroutine gets created, so practically after saying new, let's say like in a class where you are in the constructor, this initial suspend you can see as this is a suspension point before we reach the constructor's body. So the initialization, the constructor initializing this, it already ran, but now we are in the constructor's body. And before processing that further, there is a point where the compiler asks, should I continue or should I pause there? For a coroutine function, this is practically after we are calling fun. Shall it reach into the coroutine's body or pause directly before it? And my implementation here says pause first, because otherwise the coroutine would directly scream, where are you? There's a new type for doing that, suspend always. And then we have the second customization point here, which also uses suspend always, so which also is one of the suspension points, and that's yield value. Yield value here takes a std string, I copy and moves that into MSG out. So this customization point is called whenever we say yield value. And the rules for that are it's a function. So it can take any parameter we want in any shape we want it. So it can take a reference, an R-value reference, a pointer, a const reference, whatever we want. Okay, we can also have overloads. We can have multiple yield values. If our coroutine supports that, they can even be of different types. It's totally up to us. When we have array transform in G, we need that, in my case, because I'm saying co-wait here. So this is called when we are waiting for something in my special case. And I picked up a pattern here when it comes to coroutines. Inside this await transform, I'm declaring a new struct awaiter in H here. And this is 3 member functions: await ready, await resume, await suspend. These are the same member functions that suspend always implements. There's also a suspend never. So this is the full-blown implementation here, where the compiler asks, are you ready? It tells us when we get resumed. So this is where I move the value out from the wrapper type into the coroutine, where it then gets resumed. And there's an await suspend, which currently does nothing, but we will see an example for that later. And then we have the operation of this awaiter here. I'm passing reference to this and storing that to later get the message. We can move this awaiter out, but I picked the pattern to put it in there because usually it has no meaning outside this await transform. And then finally, we have the 2 remaining customization points to make this coroutine work. Return value, that's equivalent to yield value. So it's a function. It takes parameters or 1 parameter. The difference to to yield value is return value always returns void. So there is no question the compiler asked whether this coroutine should be paused at this point or not. It will always be paused. But I have the option here to take values and store them in the coroutine. And the final point really is final suspend. This is before the coroutine really ends and everything gets freed. This is final suspend. So there we can also customize, shall the compiler or the implementation pause there for our coroutine, or shall it flow off the end. So this is our promise type. Once you grow to coroutines, it becomes easier, but I guess that initially it's a lot. Here is the wrapper type, my coroutine or my wrapper type chat. In line number 2 up there, I'm doing something else I'm usually not doing. I'm hard including the promise type.h header. So imagine this is what you viewed on the slide before. This goes directly in there because the 2 types know each other. In A, I'm creating a handle of a coroutine. So coroutine handle typed with my promise type. So this is a new type in the standard library in the coroutine header. And then I have my constructor here in B, single argument, takes a promise type by reference. And in the coroutine handle, there's a static member function from promise. So I can call a function to convert a promise type, a reference to a promise type, into a coroutine handle. This is a static member function. The compiler or the machinery has an internal mapping table to get from a promise type to a coroutine handle and vice versa. So here I'm simply storing the coroutine handle. Because of this handle, because we are practically looking at a pointer to dynamic memory, this class is not copyable. This is why what I'm achieving in C here by implementing the move constructor and swapping the data once it's invoked. And I'm disabling the copy operations with that, right? So this is what I'm trying to do here. There might be cases where you want your coroutine to be copyable, but remember, it's like a pointer pointing to dynamic memory that's stored inside this data type, and we know all that's very difficult to copy, or we should be careful with that. Because of that pointer thing, there is a destructor in DDEM that one checks whether the coroutine handle is still valid, and if so, it calls destroy on the handle. So we have to do this operation specifically. And then there are now the two member functions that you previously only saw used. Listen checks whether the coroutine is not already done yet. So it did not co-return. So we are allowed to resume it. And if so, it gets resumed. And then in line number 19, I'm using the handle to get hands on the promise type and then pull the std string that's stored inside the promise type out to the use function such that it can be couted. Answer is the other way around. I'm storing the just received std string in the promise type, checking whether the coroutine hasn't finished, and so it gets resumed. So this is my entire coroutine. In a picture, from the left to the right, we have our user code. So this is from the function use, where I call my coroutine fun, where I call listen, where I call answer, and listen again. So this is user written code. And then in the middle, I have my type chat, so my wrapper type. And that internally must contain a promise type, whether it contains storage space or T or for multiple T's, in my case, to std strings. That's optional to the compiler. It might be vital for our implementation, but the compiler has no saying there that it's required. The member functions that chat comes with, listen and answer, these are my designs. So you can go totally free of them. You can name them differently. It's up to us. That this coroutine stores this wrapper type here stores the coroutine handle. That's optional. We will later see an example where it doesn't do that. For my coroutine example, it's necessary. This coroutine handle then points us to the thing on the right. So this is our coroutine. And in there you can see we have the coroutine code. So this is the code for my function fun. And that one gets heavily transformed by the compiler. So one example is all the local variables, including the parameters we are passing to the function, are not on the stack. They get rewired to point to the coroutine frame on the heap, okay? And every co-yield reaches into the promise type's yield value and so forth. If you're interested, I don't have time today, go over to C++ Insights and turn on the coroutine transformation. I put a lot of effort in there to visualize coroutines as well, so that might help you. But maybe in the Q&A later we have time to do that if there's a specific appetite, but not during the talk. So this is the coroutine chat. Okay, first coroutine, excellent. Let's have a few definitions for the rest of the talk. I will refer to a task as a coroutine that does a job without returning a value. And I will refer to a generator as a coroutine that does a job and returns a value, either by co-return or co-yield, whatever is necessary. A couple of other things here. You've already seen suspend always. It's a new type that's available in C++20 standard library together with std suspend never. These are the types that usually are returned from yield value, initial suspend, final suspend. The default implementation here for await ready is returning false, and for suspend never, it's returning true. The two other functions, await suspend and await resumed, are simply empty. We can customize these types, implement them ourselves. These are yet another customization points that the compiler looks for in the type. Okay, so it doesn't border that it must be derived from suspend always or suspend never. You can have a totally unrelated type as long as the member functions are there, spelled like here on the slide. All right, so let's look at more tasks coroutines can do for us, or we can do with them. Interleaving two std vector objects. That's a fun thing to do, right? So what I mean by that is I have a vector A and the vector B, always come with a couple of numbers, and I want print one of A, one of B, one of A, one of B, and so forth. So interleaving them together such that a sequence as shown below here, is the output. How do we do that? Well, here's a coroutine interleaved. It returns a generator type. So looking at the body of this function, we can see there's a co-yield. So we know it's a coroutine. So generator obviously must be wrapper type. So there's a promise type inside generator. Interleaved takes two stood vectors by value. And then I managed to squeeze lambdas into this coroutine talk. Lambdas can be coroutines as well. So in line number 3 here, I have this lambda lamb, which takes a stood vector by reference and returns a generator. So the same type my coroutine interleaved returns. The lambda does nothing more than looping over the stood vector and yielding value by value. So this is one excellent point of a coroutine. It can simply yield a value, go to sleep, yield the next one, go to sleep. So it preserves the state where it left off. Excellent. In line 7 and 8, then, I'm creating two new objects, x and epsilon, by invoking the lambda. So here I have two coroutines, x and epsilon. And now we can see they come with a couple of member functions. My wrapper type comes, one of them is finished, and the other one is value, and the third one is resume. What I'm doing here is, and this is another pattern that you will see often when it comes to coroutines, I have a while loop, most likely an infinite loop. And this while loop here checks that neither x nor epsilon is finished, or at least not both of them. And if so, it goes into the while's body and it checks again, is x not finished? All right, then co-yield the value from x, and after that resume x. Next thing is do the same for epsilon. So this is printing a value of a, printing a value of b, printing a value of a, and b, and so forth. Should one of them be empty, only the values of the remaining container is printed. How does the wrapper type and the promise type look? Here you see the promise type of my coroutine generator. The promise type, this time in line number 2, stores an integer underscore val. The get return object customization point returns a generator, same pattern as before. Initial suspend now says never. So this is a difference to before, because I want to get the value out of the stood vector once I start a coroutine. This is due to the pattern that I first yield the value and then I resume the coroutine. That's interesting for ending that entire thing, and you might find other ways to implement it, but this is the most easiest one I found for this example. File suspend that yield value, say suspend always. Yield value takes over the value and stores it. There is a new customization point in line number 13 we haven't seen before. This is return void, because the coroutine I just showed you can flow simply off the function. There is no co-return for a value, but our while loop may end. So this is where we need a customization point return void, simply to indicate, yeah, this is called when we flow off the end of the coroutine. We can do something there. I don't need it. So this time a promise type is shorter than the previous one. My generator now looks like this. I once again store a handle to the coroutine, the promise type. Same pattern here. I have a constructor taking that promise type, converting it to coroutine handle. It's only movable. This is done in line number 6. I am ensuring that everything gets destroyed properly in the destructor in line number 8. I have this function val to make usage more nice, which reaches via the handle to the promise type, grabbing the value. I have this function finished here in line number 15. This is just a nicer way of calling coroutine handle.done. And the function resume always checks whether the coroutine is not finished and only resumes the coroutine in that case. So this is my wrapper type. Shorter, I would say, again, as the last one. We can use this now by saying, okay, I have this std vector A and this std vector B. I'm creating a new object G of type generator, calling my coroutine interleaved here in line number 6, moving these two std vectors into the coroutine, and then in line number 8, I have this while loop, which loops as long as the coroutine generator is not finished, and it couts by calling g.value. And after that, it calls g.resume. So this is interleaving two std vectors. It's a good thing. It works, right? I would say. However, looking at this piece of code, it's mine. I can judge it. You can too. It's not the best code, right? There are implicit assumptions. So value has to be called before resume and so forth. So this is not brilliant. We are not doing something nowadays, right? So I would say the next task is we need a plastic surgeon, and one for software, not for human skin this time, because I'm sure we all would like to use a range-based for loop here instead of this, well, very ugly looking while loop, right? So let's see what we have to do for achieving that. For an object to be usable in a range-based for loop, the object must satisfy the iterator concept. So better, the function must provide the two member functions begin and end, and the types they return must satisfy the iterator concept. So that means here my iterator part comes into play. My iterator stores a coroutine handle of my promise type. I'm implementing the operator equals. Usually the concept requires the not equal operator, but in C++20, the compiler is smart enough to flip that around. So I'm on the positive side, implementing the operator equals equals. That one takes a std default sentinel. So this is just a tag type to get a machinery done because the coroutine knows when it's finished, right? We can call the handle.done. So no need to compare it to something. Then I'm implementing the operator plus plus here, which resumes the coroutine and then returns a reference to the iterator. And finally, I'm implementing the star or dereference operator, and that one fetches the value from the handle via the promise. And then we are done. So this is my iterator part. And the last thing that's missing here is to say, okay, inside my class generator, I implement begin and end, the two member functions. Begin returns an iterator type, end returns a std sentinel t, and in begin I'm creating the iterator by passing the current coroutine's handle. This makes using the coroutine much nicer. The lines 1 to 4 are the same as before, but line number 6, now I can use a range-based for loop, iterating over g, getting each value in the form of e, and couting that. So I no longer have to know about whether to call resume or value first as a user. So I think this is what you're going for if you're implementing coroutines. Okay. I think we have time for another task. And what task would be nicer than scheduling multiple tasks, right? I mean, I cannot do a second talk here in parallel, but I think my computer would be able to do that. So multitasking. We have cooperative and preemptive multitasking. With preemptive multitasking, the thread has no control over when it runs, on which CPU it runs, or for how long it runs. I was in a situation where it was very vital that the thread did run on a certain CPU. It was very hard to achieve that. In cooperative multitasking, the thread decides how long it runs and when it is time to give control to another thread. So this is a total different pattern. It means we do not get interrupted unless we give up. So way less locks we have there or we require there compared to preemptive multitasking. We can say that in cooperative multitaskings, the locks are equivalent to co-yields and co-waits, because this is when we give up control. The problem is a task can run for a very long time without getting interrupted. And this might be something that's not the right thing for your environment. But if you can accept that if the time is short enough. Coroutines are a real interesting thing. So let's have a look. I want to schedule multiple tasks. So say I have this function use here. It has a scheduler object declared, and then I create these two tasks, A and B. I pass the scheduler to it, and afterwards in line number 8, I'm calling scheduler.schedule to simply schedule the tasks until everything is done and my program ends. A very, very simple thing. So here are my two tasks, also simple. Task A and task B, they are totally equivalent except for the text they're printing out. The one says always I'm task A and the other one says task B. So nothing special there. The two tasks return a task object because we can see a co-wait inside this function. We know it's a coroutine. We know task contains a promise type. They both get the scheduler passed by reference, and they print out a value with cout, and then they're co-waiting on the scheduler calling a member function suspend. Okay, so this is how they suspend and give the other one a chance to continue processing. And they do this 3 times, and after that, everything is finished. Think of, instead of couting, you might read something from the network, a file, or something like that, and you pause because there's a stall and you give up to the other side. Here's my scheduler. Very simple one. It uses a std list coroutine handles, and this time we are looking at void coroutine handles. So we can have a type erased coroutine handle. That means we don't know the exact promise type, but there's no reason to do that because remember it's a task, so it doesn't return any value or yield any value. So there's nothing we need to know about this promise type. A void one, a base one, so to speak, is enough. So this list of coroutine handles I call tasks. Then I have this function schedule here. It pops the first element from the list, checks whether this is done or not, and if not, it resumes the coroutine, and as a result, it returns whether the tasks this to the list at this point is empty or not. So are there more tasks to being scheduled? The member function suspend implements an awaiter, so it's a different version of the one we saw before. This one I'm deriving from suspend always. This is another pattern I picked up. It's nice to see what the default is. So this is just a modification of suspend always. I'm storing a reference to the scheduler in it. This is why, because of the inheritance now, I need a constructor here to process this reference. And the only thing I'm overriding from my suspend always is the function await suspend or the customization point. This time I'm interested in the coroutine handle because this function gets invoked before the coroutine goes to sleep. And I'm using this coroutine handle to push it back to the task list in the scheduler, such that it is there and gets resumed the next time it's its turn. Then suspend here returns such an awaiter, passing the dispointer to it for the scheduler, and we are done. So it's a very, very basic and maybe dumb scheduler, but it works very well. This is our wrapper type. Now here you have the promise type. It might be the shortest promise type you will find, including the wrapper type here, task. Task has no member functions because it doesn't store anything. The promise type is reduced to only the customization points we require for our example. They all practically do nothing because we have no co-yield in it and nothing else. The co-wait is deferred to my scheduler practically. I have a return void there. I don't handle exceptions and so forth. Get return object is also easy because I have a default constructor in there. So everything is very simple. So this is scheduling multiple tasks with a coroutine. Okay, a very, very simple scheduler here, very simple system. But they get not interrupted. This is a major point here. No logs. Perfect. But maybe we want to do things differently. Maybe not every task should know about a scheduler. So what if we want to do it like this? We have the two tasks A and B, and we simply want to spawn them and then have our gscheduler and call scheduler that in the while loop. So gscheduler should hinder this is a global object this time. You can decide what you want, but let's have a look how this would look. It would change our two tasks. They obviously would no longer take a scheduler reference as a parameter. So that means internally, they can all either reach to the global scheduler, but the idea is to abstract that one. So I'm co-waiting and creating a new type here or a new object of this type suspend in co-wait. So all the time I'm creating a new temporary object, co-waiting, and I get resumed. My scheduler looks a little different, but nothing really has changed. I have still a stood list of coroutine handles, of void coroutine handles called tasks. I have this new member function suspend. It's just to make things a little easier. That one takes a coroutine handle and it pushes it back to the task list. Schedule is as before. I'm grabbing the first task in the list, checking whether it's resumable. If so, I do resume it, and I return whether the list is empty. So my entire tasks are finished doing their work or not. This here now is the part we need to make co-wait useful. So in line of one, you can see I'm declaring this gscheduler object of type scheduler as a static. And then I'm having the struct suspend here. And suspend implements a operator co-wait. So this is something we also got new in C++20, a new operator called co-await. This one is invoked when I say co-wait on this type or an object of this type to be precise. My awaiter here derives from suspend always as before, and because I this time do not have to pass any reference or any data to it, I don't need a constructor, I don't need data in it. I simply override a customization point await suspend. That one takes the coroutine handle and passes it to the scheduler, putting it at the end of the list. I'm creating an object of this awaiter struct and return it, and I'm done. So this is a different approach of implementing something that schedules your multiple tasks. This is a very interesting to note concept of coroutines, since we from the outside control this coroutine once it gave up control. We have to resume it, otherwise it simply sleeps there. So when it comes to coroutines, there is always some kind of scheduling involved. So some machinery that resumes the coroutine, that it checks whether it should take the other one or this one, resume, or pause. So one way or the other, we have some kind of scheduler in the background. It might be something way simpler than you just saw here. Maybe something like from the chat example where you simply communicate with this coroutine. But you can also have a scheduler like you saw it here, or an even more sophisticated scheduler that maybe implements priorities for your different tasks, stuff like that. Okay. There are some restrictions or limitations when it comes to coroutines. So context functions, for example, cannot be coroutines. Subsequently, this is true for const eval functions. A constructor and a destructor cannot be a coroutine. I mean, what would that mean, right? So a half constructed or half destructed object sounds difficult. A function using var args cannot be a coroutine. Do not confuse that with variadic functions in C++11 and later. They work because they are function templates. Or function templates, I should say precisely. Var args means you're looking at what came from C with preemptive, where you have a variadic function that uses the stack to achieve the variadicness. The variadic function template is simply a function that's unfolded with all the parameters, so that one works. A function with plain auto as a return type or with a concept type cannot be a coroutine. Auto as a trailing return type where we omits the type deduction, that works on the other hand. Also, to sadness of a lot of people, a coroutine cannot use plain return. You either have to say co-return or co-yield at this point. And last but not least, main can also not be a coroutine. Same thing as for constructors and destructors. What would it mean to have the program started and not really started? Lambdas, on the other hand, and you saw that in my talk, can be coroutines. But because lambdas by default return auto, this is why I use the trailing return type from a lambda in the interleaved example to tell the compiler the return type of my lambda. So this is why I use the trailing return type there. No plain auto when it comes to coroutines. All right, excellent. So with that, I'm at the end of my presentation. I will head over to GatherTown to answer questions there. If I gained your appetite for coroutines, I'm giving a workshop together with cplusplus online on Monday. So in 2 days about coroutines. We will do more than we just saw today in the talk. So there will be also stuff like dynamic memory allocations for your coroutines, how to control that. We will do comparisons to threads and a lot of more fun stuff. So if you're interested, it's still time, I think, to sign up. Feel free to do so. You can also subscribe to my newsletter and grab the coroutine cheat sheet. I try to give you a very brief and dense overview about coroutines and how they work. In my book, Programming with C++ 20, I dedicated one chapter solely to coroutines. So this just came out with the second edition. This can also be some good point to learn more about coroutines. I hope you enjoyed it. All that's left to me to say is I'm fertig. Thank you.